Very good morning to one and all. This is Dr. C.H. Rajendra Prasad, Associate Professor, Department of ECE. I welcome you all for video lecture series on microcontrollers and applications. Today I am going to discuss arithmetic instructions of 8051 microcontroller. The 8051 microcontroller supports a set of instructions to perform the arithmetic operations. The set includes ADD. ADD stands for addition. ADDC. ADDC stands for addition with carry. INC. INC stands for increment. SUBB. SUBB stands for subtraction with borrow. DEC. DCE. Decrement. DEC stands for decrement. And MUL stands for multiplication. DAV stands for division. DAA stands for decimal adjust for addition. These are this set of instructions supported by 8051 microcontroller to perform arithmetic operations within the 8051 microcontroller. Let us see one by one. The first one is add instruction. Add stands for addition. The syntax for addition is ADD A comma source. Here source may be register, memory, or any immediate number, but the destination is always accumulator. As we know that the 8051 microcontroller is accumulator based microcontroller. The accumulator based microcontroller means after performing any arithmetic or logical operations, the result is always stored in a accumulator. So that's where the 8051 microcontroller is called as accumulator based microcontroller. Coming to operation of this addition instruction, the addition instruction adds a register contains with the source specified within the instruction, and the result is saved in accumulator and carry flag. Why we are use this carry means here when you perform addition of two 8-bit numbers, we are getting 9-bit sum, 9-bit result, 9-bit sum or 9-bit result. But we are having only the accumulator is acting as a destination. But to store the 9th bit information, so the carry flag is used, which is available within the PSW register of 8051 microcontroller. So combinedly we need to read like this. The result is read like this: carry and accumulator value, total 9 bits. The carry and accumulator value we need to read. This is total 9 bits result. Let us see one example how the 8051 microcontroller performs the addition of two 8-bit numbers. So let us consider a first number FF, FFH. The binary equivalent of FFH is 8 ones, and let us consider one more number 11H. The binary equivalent of this 11 is 0001 and 0001. When you perform the addition and let us assume before execution of this addition operation, accumulator contains this FFH, and the source operand contains this 11H. When you perform addition of these two numbers, we need to perform the addition now. 1 plus 1 0 and carry 1, and 1 plus 1 0 carry 1, 1 plus 1 0 carry 1, 1 plus 1, 0, carry 1, 1 plus 1, 1 0, and 1 0 plus 1, 1, carry 1, here 0, carry 1, 0, carry 1, 0, carry 1. So if you observe our result, this is our 8-bit result which is stored in accumulator, and the 9th bit information that is stored in the carry flag. So that means we are getting 9-bit sum. Some cases, if based on your inputs, the carry may not be generated, it may be 0. So in that case also our result will be available in carry and accumulator only, but carry flag value will be 0. Carry flag value will be 0. Now then we need to, after this addition, we can also check the status of the processor with the help of status flags. The status flags already we know that they are available in PSW register of 8051 microcontroller. They are carry flag, auxiliary carry flag, parity flag, and overflow flag. So already we know that the result is available in accumulator is now 1 0, and the carry flag is equal to 1. Here the carry flag is equal to 1 already. We know that. Then after addition or after subtraction, if there is a carry generated after the label, auxiliary carry flag will be set to 1. AF will be set to 1. Auxiliary carry flag will be set to 1. And similarly, the 8051 also checks the A register contents, that is the number of ones in the accumulator. So the number of ones in the accumulator is odd number, then the parity flag will be set to 1. The parity flag will be set to 1. Why? Because here in 8051 microcontroller follows the odd parity. So here result contains the odd number of ones. One is available as one number. So odd number. It is odd number only. So the parity flag is set to 1. And one more important thing, important flag is the overflow flag. But this is equal to 0. Why? Because here there is a carry is resulted from 7th bit to MSB, and there is a carry is resulted from MSB to carry. But the overflow flag will be set to 1 only any one of these two conditions are satisfied. But here in this case, the two conditions are satisfied. That means it is equal to 0. The final status is now carry flag is equal to 1, auxiliary carry flag is equal to 1, parity flag is equal to 1, overflow flag is equal to 0. This is the status of the 8051 microcontroller after performing addition operation on these two numbers. Okay, so now once again you can see now. So here carry flag is set to 1, auxiliary carry flag is set to 1, parity flag is set to 1, and overflow flag will be equal to 0. But our final result is available in this 1 0 is available in accumulator, the 1 is available in carry flag. The final result of how we can read our result 1 1 0. Here 1 0 is available in accumulator. This only single bit is available in carry flag. So our actual 9-bit sum is this one. Okay. So this is the operation of add instruction. Next we need to consider the ADDC, addition with carry. Addition with carry. So the syntax is similar to add instruction, ADDC A comma source. Here source is also a register, memory, or any immediate number. The operation is also same, except here when you are using addition with carry, the previous carry also added to the sum, and the result is saved in accumulator and a carry flag. So here also we are getting 9-bit result. The 9-bit result is stored in carry flag bit as well as accumulator. And next instruction is increment. INC stands for increment. The syntax for increment is increment the destination, where the destination may be any register or a memory location, but it cannot be a immediate number. Why? Because we cannot increment the a number, a constant. So that's where here the destination is always a register or a memory location. So let us consider one example here. In this example, we are incrementing the value of R0 register. Let us consider R0 register is having some value, that is 11H before execution, but after execution of this increment R0 instruction, increment R0 instruction, the value will be incremented by 1. That means it will be 12H. This will be 12H. Before execution it is having 11 only, but after execution it is incremented by 1. So this is the operation of increment instruction or increment R0 instruction. Increment 58. So if you consider this example, in this example we are considered the memory location. Here 50 represents memory location. That memory location belongs to internal RAM only. So let us consider this is internal RAM location 50, internal RAM location 50, where let us consider some 14H is available in this location. And when you before execution of this instruction, this 50H location is having 14H data, and when you execute this instruction, the 50H location content is incremented by 1. That means after execution of this instruction, it becomes 15H. 14 is incremented by 1 means it is 15. So now the value available in 50H location will be 15 after execution of increment 50H. And similarly, we can take one more example, increment at the rate R0, where we are representing memory location indirectly within the instruction to a R0 register. Now R0 is acting as a pointer. So let us consider R0 is pointing to 50H location. Before execution 14 is available. After execution of this instruction, it becomes 15H. So this is the operation of increment instruction. Then we need to go for next instruction, that is subtraction with borrow. Let us see subtraction with borrow. Now you can see SUBB. Here we are using only one instruction for subtraction, that is subtract with borrow. The syntax for this instruction is SUBB a comma source. Here also source is register, memory, or any immediate number. The destination is always accumulator only for all arithmetic and logical operations. And while performing the subtraction operation within the 8051 microcontroller, the 8051 microcontroller uses the 2's complement addition method. Let us see first how what is the algorithm we need to follow for 2's complement addition. In 2's complement addition, we need to follow the a procedure. That procedure is having 3 steps. We let us consider these 3 steps. First, the first step is take the 2's complement of subtrahend, then add it to the minuend. The subtrahend should be added to the minuend, and then invert the carry. So these are the 3 steps we need to follow when you are using subtraction by using 2's complement addition method. And one more important thing, the operation of subtraction operation is, if you observe here, the source content and previous carry is subtracted from accumulator, and the result is saved in accumulator itself. But based on the size of the source operand, the carry may be set to 1 or reset to 0. If the source is greater than accumulator, the carry flag will be set to 1. That means we require the borrow. We require the borrow. Otherwise, the carry will be equal to 0. That means A is greater than source. When A is greater than source, we don't require any borrow. So whenever we don't require any borrow, the carry flag will be equal to 0. And while performing the subtraction operation, we need to follow these 3 steps. Why? Because in 8051 microcontroller, there is no subtractor circuitry. So it uses the adder circuitry to perform the subtraction operation, but it follows the 2's complement addition method. So let us, to clear this one, let us take one simple example. The simple example consists of minus, sorry, 1 and minus 2, 1 and minus 2. That means we need to subtract 2 from 1. So where this 2 is the subtrahend, 1 is the minuend. This is minuend and this is subtrahend. So that means first we need to take the 2's complement of subtrahend. To get the 2's complement of subtrahend, first we need to represent 2 in binary format. After representing 2 in binary format, then we need to take the 1's complement of that number. So the 1's complement is simply invert each bit of the 0 to. So after inverting this, we are getting this number, that is FEH. Then we need to add 1 to the 1's complemented number to get the 2's complement. So the 2's complement of this number is Fe, that is equal to minus 2. So now I am getting minus 2. After getting minus 2, then we need to add, as per our algorithm, we need to add this 2's complement number to minuend. So what is our minuend? 1. So convert this 1 into binary value. This is the binary equivalent of 0 1, that is minuend now. The subtrahend value is this one. So now directly add these two. If you add these two, uh, we are getting this number. We are getting this number, and here you can observe here there is no carry. There is no carry. But as per our algorithm, we need to invert this carry. We need to invert this carry. So that means after the subtraction operation, the value of carry flag is equal to 1. The value of carry flag is equal to 1 means we require the borrow. So it is common. Why? Because 1 is less than 2. That means we require the borrow. So that means here it will be equal to 1 only. And our result available in accumulator is all ones. All ones is nothing but FF. FF is in decimal is equal to minus 1. So this is our answer. Okay. So I think you may clear the subtraction operation with this example. And next we need to move on to one more instruction, that is decrement instruction. Decrement instruction is also similar to increment. The syntax for decrement is decrement destination, where destination may be register or any memory location only. Here also, and the operation is similar except increment. Here it is decremented. So let us consider one example, R naught. So let us consider before execution of this instruction, R naught contains 1 1 1. After execution of this instruction, sorry, here it is DEC only. This is DEC, decrement or not. Decrement or not. Decrement or not. Uh, let us take one simple example. R naught is having 1 H before execution. After execution of decrement R naught instruction, the R naught value is decremented by 1. So that means R naught will becomes 10H after execution. So I think you may clear this decrement instruction operation. Then we need to discuss one more instruction, that is multiplication instruction. So this, let us see multiplication instruction. The For a multiplication instruction, the syntax is mul AB. One more thing you need to remember here. Before discussing this instruction, first we need to know, when you multiply two n-bit numbers, our product size will be 2n. That means when you are performing multiplication of two 8-bit numbers, our product size is 2 into 8. That means 16 bits. So that means here, for multiplication and division operations, the in 8051 uses the 8051 microcontroller uses the A register and B register combinedly to store the product. How it will store, we will discuss now. And one more important thing, before execution of mul instruction, one of the operand should be available in A register and another operand should be available in B register. And after then you need to perform the multiplication operation. When you perform the multiplication operation, A is multiplied with B and the result is saved in B and A register. B and A register. That means, let us consider one simple example here. 1 1 and 2 2 is multiplied. 1 1 and 2 2 is multiplied. So then, if you observe here, 2 plus 2 into 1, 2 only, 2 into 1, 2 only, then 2 into 1, 2 only, 2 into 1, 2 only. So then our product will be 2, 4, 2, and there is no digit is here. So you can simply place a 0. Then here we are, before execution, I placed A with 1 1, B with 2 2, and the result is we are getting 0 to 4 2, where the B register contains the 0 2 and the A register contains the 42. That means A register always holds the lower lower product, and higher product is available in B register. So this is the operation of multiplication instruction mul AB, and after execution of mul instruction, only overflow flag will be affected, and this overflow flag is also depends on this B register value. If the B register is having non-zero product, then the overflow flag is equal to 1. Overflow flag is equal to 1. Otherwise, it will be equal to 0. That means B register should have 0. If B register is having 0, means overflow flag is equal to 0. If B register is having non-zero value, it will overflow flag will be set to 1. So this is the operation of multiplication instruction. This is the operation of multiplication instruction. Let us see, now we need to move on to division. Before division, first we can see now the operation. Here A and B is multiplied, the result is saved in B and A register, and so we are consider one example here. After before execution, A is having 1 1, B is having 2 2. After execution, B in A register hold the product. So the product is having 0 2 is available in B register, and 42 is available in A register. And in this example, B is non-zero value, so that means overflow flag will be set to 1. Here, overflow is 1 if B register is having non-zero result. So B register is having non-zero result, so that's where overflow is equal to 1 in this example. Then we need to move on to division. So div stands for division. The syntax for division is divab. For division also, the 8051 uses B register along with A register. And so before discussing the operation of this division instruction, let us take one example. For division of 13 by 3. So 13 by 3. 13 by 3 means 13 4, 3 4 ja 12, and we are getting the remainder is equal to 1. The 8051 performs division operation like this only, and that means before execution of division instruction, first you need to place the dividend within the register, and the divisor should be available in B register. And after execution of this division operation, the quotient is placed in accumulator, and the remainder is placed in B register. So in this way, the 8051 microcontroller performs the division operation. And one more important thing, when you attempt to divide by 0, overflow flag will be set to 1. When you attempt to divide by 0, overflow flag will be set to 1. So this is the operation of division instruction, 8051 microcontroller. So let us see the operation once again. Here you can see operation is A divided by B, and the result is quotient and remainder. It will come in a quotient as well as remainder manner. The quotient is always saved in accumulator register, and remainder is always saved in B register. And let us consider a simple example now. So here I am considered A is equal to 10 H, B is equal to 0 3 H. So before execution, A and B registers are having these values, but after execution we are getting A is having 5, this is quotient, and the remainder is 1. So here 1 0 means 16. So 16 divided by 3 means 5 is the quotient, remainder is equal to 1. So, and one more important thing, when you attempt to divide by 0, that means B register is having 0. So that means the result is not fit in the accumulator. Why? Because when you divide any number with 0, we may get infinite quotient value. So that means we cannot accommodate that infinite quotient value within the finite register, that is accumulator. So that's where it will show an error with the by setting overflow flag is equal to 1. Overflow flag is equal to 1. Overflow flag is set to 1 if the B register value is equal to 0. So this is the operation of division instruction. To move on to decimal adjust after addition instruction. This instruction only works on A register only. And one more important thing, we need to use DA instruction only when you are performing the addition operation on decimal numbers. So actually, suppose for example, let us consider I am assuming a numbers, my two input numbers are 1 2 and 1 9. These are my two numbers. I am assumed these two numbers as decimal numbers. Okay, I am assumed these two numbers as decimal numbers. When I am assumed these two numbers are decimal numbers, so my result will be 1 carry 1 and 3 is my result. 31 is my result. But when you are giving same inputs to your microcontroller, it is considering these two numbers as hexadecimal numbers, hexadecimal numbers. But in hexadecimal numbers, the result will be 12h plus 19h. The result will be 9 plus 2 means 11. 11 means it is B. And 1 plus 1, 2. So our result will be 2BH only. But my requirement is, I am assuming that my two inputs are BCD. BCD means decimal numbers. And I am expecting my results is also in terms of decimal only. But your controller is giving some wrong results. To correct my results, normally we will use decimal adjust for addition instruction. This instruction will correct whatever the content is available in here is converted to original BCD form. So this is the use of decimal adjust after addition instruction. So let us see the operation of this instruction. We'll also discuss with one example. Okay. So let us see now. It is always used after add instruction or addition with carry instruction only. The operation is, it will check the lower nibble is greater than 9 or auxiliary carry flag is equal to 1, adds 06 to the lower 4 bits or 06 to the result. 06 to the result. And then after adding 06, after checking lower nibble, then it is checking the higher nibble is greater than 9 or carry flag is equal to 1. Then it will add 60h to the result. Here once again we will see the operation. First it will check. First it will check lower nibble. Is it greater than 9 or auxiliary carry flag is equal to 1? It will add 06 to the result. That means accumulator contains. And again after adding 06, then it will goes to check for higher nibble. If higher nibble is also greater than 9 or there is a carry flag is set to 1, in that case it will add 60 to the accumulator content to correct the result. So let us take one simple example to understand this one. So let us consider our number is, first number is 29, second number is 18. So here 29 plus 18 in hexadecimal we are getting 41, but in BCD we require this value. Okay, BCD we require this value. So suppose now you can see here in this application, in this example, if you observe here 1 plus 1, 1, 0, 0. But here 1 plus 1, there is a carry is generated. That means auxiliary carry flag is equal to 1. But the result available in accumulator is not greater than 9. It is, this condition is not satisfied. But auxiliary carry flag is equal to 1. That means it will add 06, 06 to the result. Here 06 means all zeros and 6 means 0110 is added. So once it is added, so the result will becomes the 0100. This is as it is, and here 6 is added. Now it will becomes 7. 40. Result is 47. So similarly, if you consider some other example, you may get the correct answer. So The DA instruction is used to correct the result after BCD addition. Okay, so from this we completed this arithmetic instructions in 8051 microcontroller. Thank you one and all for listening my lecture. Thank you.